briefly introduce myself. I did my PhD not too far from here. I usually follow that up with a walk around and go Bruins, but I have a feeling I may not want to do that. I spent a couple of years at UPenn in the Modeling Simulation Lab, followed by a stint at this research, and I started my faculty position at Rutgers, where I'm the director of the Intelligent Visual Interfaces Lab. So our research is at the intersection of computational intelligence, visual computing, and human-computer interaction, with sort of a far-reaching mission to develop intelligent visual interfaces to empower content creation. So with that in mind, our sort of lab sort of looks at research, developing computational models of human behavior, how that can be used to enhance computer-aided design pipelines, using those models to be able to sort of create immersive, interactive digital stories in these virtual worlds, and finally using play or serious games as a means and a metaphor to sort of help this overall process. So today, I'm going to talk about our research at the intersection of architectural design, human behavior modeling, and AI, towards developing solutions for intelligent, human-aware building design. So, the challenge that has been repeated numerous times, right, is being able to sort of empower designers and architects with the ability to sort of account for the truly intricate and complex underpinnings that sort of involve the movement and behavior of people in built environments. And this sort of really leads us to the question is that how can we empower designers and architects with that tool, an oracle, if you will, right, which sort of allows them to sort of predict beforehand how people can inhabit, occupy, and sort of interact with their space. So I'd like to argue that current tools provide only a static representation of human movement and behavior profiles, and are unable to sort of capture sort of what is at the heart of it, a truly sort of a dynamic and sort of complicated sort of coupling, right, between how people move and behave and in this space. So this is sort of prevalent in current design pipelines, which are crowd agnostic. They are unable to account for sort of these sort of crowd-related properties and characteristics, right, that architects and designers are forced to rely on only their intuition and sort of expert guidance, right, while designing and modeling environments. So this leads me to my question, is that how can we represent buildings in use? So going back to this traditional pipeline, right, we sort of look at, right, all of this amazing work in sort of crowd behavior modeling and sensing and sort of behavior modeling, right, which can be used to possibly sort of supplement and enhance these pipelines, right, to facilitate crowd-aware environment analysis and sort of getting us closer to what I refer to as a crowd-aware environment design process. So, in the talks yesterday, right, so there was some really exciting and innovative tools and sensing solutions to do crowd surveillance or crowd activity tracking. However, while these tools sort of provide or give us the ability to sort of track and monitor human movement in its most natural setting, the data is fundamentally limited. It is subject to noise in the sensing, and perhaps most importantly, with these kinds of tools, interventions are fundamentally not possible. We can't set a building on fire with the hope to understand how people would evacuate that building, right? So laboratory experiments provide a viable alternative, right? However, while they sort of address some of the limitations that I pointed to, right, we are still sort of fundamentally limited in the capacity with which we can do controlled interventions. So I'd like to go back to this drawing board, right? And while this approach sort of allows us to sort of study built environments, it fundamentally falls short at the design stage and doesn't allow us to study yet to be built environments, which are still in their design stage. So I'd like to modify my question a little bit and ask, how can we represent buildings in use prior to their realization? So coming back to this evolving framework, we look at and sort of rely on some of the most excellent work that has been done, right, and was presented in the talk before, and we sort of posit that if we had the ability to develop and use data-driven computational models of human crowd behavior that captured the essence of observations that were seen before, while permitting extrapolation to new and unseen environmental conditions. We could use that to drive a joint crowd environment model, right, which can then be used as the basis for doing crowd-aware building analysis in new and unseen situations, thus truly sort of giving us this complete crowd-aware environment design pipeline. So we're getting a little ahead of ourselves, right? This is entirely predicated on our ability to sort of solve that box right there. And this sort of takes me to the first goal of my talk, my 5 minutes, which is to sort of develop computational models of human crowd behavior that sort of facilitate the simulation of functional, purposeful, autonomous virtual humans that sort of exhibit plausible and meaningful interactions with each other and with the environment that can sort of facilitate the kinds of things that I talked about. So there is a rich body of decades of research in this space, right, with researchers sort of having looked at this problem from a variety of different perspectives. However, there are some foundational assumptions that these approaches make, right? Namely, sort of using these simple particle-based representations that sort of produce some artifacts. This is not how we as humans move, right? So what you can see in these illustrations is sliding in crowded situations, live blocks and deadlocks in narrow passageways, and even violations of simple orientation constraints. So to that end, right, we've been sort of systematically sort of zooming into some of these assumptions towards deriving a proposed approach. And I only have time to talk about a few things, right? One of the solutions that we worked on is sort of moving away from these sort of simple representations of human agents and developing biomechanically plausible solutions of human crowd movement, right? Where our agents are actually selecting footsteps while moving and avoiding collisions in crowded spaces. So these solutions sort of permit our characters to sort of account for the affordances that govern bipedal movement, right, while moving in crowded spaces. So in this example, which is a simple egress, right, what we'll see very shortly is sort of these particle overlays are actually producing invalid, right, or collisions, but these bipeds are able to sort of get significantly closer together, sort of while evacuating the simple building, right? So I would like to argue, right, that these more sophisticated representations are critical when using simulations to sort of understand the relation between human occupancy and environment design. So just another illustration that sort of shows these completely autonomous characters, right, that are sort of exhibiting sort of a cooperation and fluidity when interacting these narrow passageways. So the passageway that is so small that only a single agent can squeeze through, right? So we sort of see the character in focus sort of subtly taking a side step, allowing the other one to go through while sort of maneuvering his way through, right? So these sort of natural cooperation-like behaviors sort of emerge out of our approach. So I just want to take a quick sidebar, right? So moving beyond just walkers, right, we're also interested in sort of truly simulating sort of the dexterous contact-rich movement that sort of govern what our bodies can do, right? And I'd like to argue that these solutions are also of critical importance, right, as we sort of look to sort of understand how these solutions can be used to facilitate environments of any form or shape. And all of these tools can sort of ultimately be brought together, right, and exposed to end users, architects, designers, or planners, where they can sort of use these tools, which are abstracted away using some of these graphical programming languages, to very quickly start creating simple multi-actor interactions. So this behavior, right, this conversation between these two actors, sort of was authored using the simple graphical program, right, and this sort of relies on all of the tools that I talked about before. And so with this, we can now start creating incrementally more complex things. So this is a simple narrative that was authored using our tools, right? And this was done by a non-expert, right? So basically someone within a few minutes could sort of author this animation, this narrative of reasonable complexity using our solutions. Okay, so I'm going to start speeding through because I'm short of time. So with this, we can now start doing interesting things. Right? So we can start modeling and studying evacuations and seeing how characteristics of the crowd behavior can be altered to optimize the time it would take to evacuate a building, for example. Okay? So, coming back to my comparison, right, so I'd like to argue that virtual crowds or simulations sort of offer the promise of plausible behavior while supporting unlimited interventions and what-if studies that are not possible using real data. There are a couple of asterisks on top here, right, and this is something that Professor Warren sort of alluded to in his talk, and that's something we can definitely talk about offline. Okay, so going back to my approach, right? The next challenge is, now that we have these tools, how can we use them to study environments? So to that end, we've been sort of developing these joint approaches for studying environment and crowd behavior. At the high level, right, what we do is we have the ability to sort of specify occupancy, behavior distributions, and individual motivations, and sort of use that to instantly generate plausible distributions of crowd activity in a specific space. So how does this work? So this demo is a little rough around the edges, but essentially what we're doing in our tool is an architect is using a conversational interface to talk to its building, sort of specifying that, oh, this is an office room, this is used for meetings, right? And our system is able to sort of reason about the semantics instantly. And I'm going to skip through this video and produce, so let me just go to my next video, right? So our designers can sort of use existing pipelines, right, like that Autodesk Revit, sort of provide these semantic specifications in them, and sort of instantly pressing a button sort of generates a plausible distribution of crowd activity in that environment as it is being designed, right? So this sort of provides instant feedback to the designer, which will sort of go back to the design, change the specifications, change the environmental configurations, and see if it conforms to their desired specifications. And this thing can sort of be used as post hoc analysis or to inform the current design iteration. Okay. Another useful property of this is, right, that where previously designers were sort of limited to sort of exploring their designs in virtual reality in this case, which were empty, can now be sort of instantly populated, right? So here's essentially the same sort of design, but the difference here, right, is that this VR exploration can now be sort of populated with plausible crowd activity. Okay, so just want to quickly point out, right, that we aren't limited to simulating just crowd movement. So here's a simple demonstration which was actually done using Autodesk Research's SciDef's platform, which sort of allows us to sort of jointly simulate crowd movement as well as environmental conditions such as heat expenditure in this case, right? So we can start concurrently studying these human behaviors and environmental conditions jointly. Sort of allowing us to sort of do analyses at a deeper level, right? So we can sort of start studying the influence of how the human movement and behavior sort of affects temperature in the space, and study other factors like sort of ambient noise, etc. Okay, so I have 2 minutes, right? So I'll race through this. So finally, what I'd like to say is that given the benefits of these approaches, one of the limitations that still remains, right, is that architects are sort of ultimately confined to sort of a manual exploration or sort of these high-dimensional spaces, right, of infinitely many environmental alterations and crowd characteristics. And this is prohibitive when dealing with these kinds of spaces. So to that end, we sort of take advantage of the fact that this part of the pipeline can be completely automated, right, where we can use artificial intelligence to sort of help exhaustively explore the design space of permissible environmental configurations and provide suggestions of how environments may be reconfigured. And this can then be sort of used to provide an enhanced computer-aided design pipeline that fundamentally accounts for human occupancy. And that brings me to the last goal of my talk, which is how can we sort of empower designers, right, with the ability to efficiently explore. And I see my slide moving on its own now, which is probably an indication that I'm out of time. So this is the solution. So our solution essentially, again, integrated within existing practices, right? So as designers are designing their space, our system is running simulations behind the scenes, right, to essentially automatically score their environment, their current design with respect to any human crowd occupancy criteria, and suggesting permissible reconfigurations to their design, which they can then review in real time and sort of account for in their design process. Okay, so that's essentially sort of the potential of sort of using all of these crowd simulation tools that can be integrated within CAD pipelines. So I'm going to skip some of this in the interest of time. And I'll just highlight a couple of interesting results, right? So we use these tools to optimize or to help design a portion of the Metropolitan Museum of Fine Arts in New York, right? So in this illustration, so the optimized design is on the bottom, so we can sort of see that making these subtle changes in how these walls are configured, right? We can sort of maximize the visibility and accessibility of these different paintings and exhibits along the passageway. We can sort of minimize the congestion in sort of the central corridor, and these are things that sort of can automatically be discovered by our CAD pipelines while still keeping the designer sort of firmly central in the design. We also use these same solutions to sort of help sort of reconfigure the design of the NYC Penn Station subway. This was a discussion that we had yesterday, right? So in this case, we were once again trying to sort of minimize congestion in the narrow subway, right? So while maximizing the accessibility of the stairwells in the event of an evacuation. We aren't limited to simply moving walls, right? So we could use these same tools to, for example, optimize signage, right, in large complex spaces. So we did 2 case studies with a real shopping mall and train station in Singapore, where we effectively used our tools to help inform how signage may be sort of reconfigured in a space, right, to sort of minimize the confusion or getting lost in the heart of these buildings. Okay, so I apologize, I think I ran over, but to conclude, right, so we've looked at how we can sort of move beyond existing crowd-agnostic design pipelines to solutions that are crowd-aware and potentially relying on artificial intelligence to sort of provide enhanced CAD pipelines. So with that, here's some of the funding that's made all of this research possible. A quick shout out to all of our collaborators, without which this would not have been possible, and thank you so much for your time.